Good morning, everyone. Hi again for one of our online lectures. Today's topic is duality. So I'll be talking about I'll first explain what duality is, and then maybe if time permits, we will also start talking about the duality theorems. Okay, duality is one of the most crucial topics in optimization, and you will see why when we're done with this. All right. So let's take I have already shared my screen and everything. So let me start to go over what I have here. All right, but why is it not changing this? You guys still see the duality, even though I did change. Oh my gosh. Oh, here it is. Okay, sometimes it takes time. Sorry. Okay, let's focus on this LP in here, okay? Maximizing 2x1 plus 3x2 subject to three sets of constraints, okay? The first constraint is 4x1 plus 8x2 less than or equal to 12, 2x1 plus x2 less than or equal to 3, and 3x1 plus 2x2 less than or equal to 4, okay? And both variables are non-negative. This is a basic two-variable LP. Now, yes, of course, we can solve this via all the methods that we have already learned, but how about we try to come up with a bound? This is a maximization problem, right? So how far can this objective can go up to? Like if somebody gives me a solution with 50, how can I judge it? Is it optimal, not? Is it good enough? How can I judge it? Okay? So, well, the thing that you could utilize is, first of all, any x that can be a solution for me have to satisfy all these constraints, right? They have to be in the feasible region. Now, let's focus on the first constraint right now. It says 4x1 plus 8x2 cannot be more than 12. Now, look at the objective function. Objective function is 2x1 plus 3x2. If I multiply the objective function by 2, I'm going to get 4x1 plus 6x2, right? Well, this is definitely less than or equal to 4x1 plus 8x2 because everybody is non-negative. And I know this is less than or equal to 12 because that's my constraint, right? So my objective can never be larger than 12, right? Because a portion of it is bounded by it. Or let's look at the second constraint and what can I do to make it similar to my objective function? Well, if you look at it, 2x1 plus 3x2, well, from the second constraint, no, it's still from the first one. If you multiply the second constraint by 1.2, you're going to get 2x1 plus 4x2, which is still larger than my objective function. So apparently, I cannot be more than 6, right? Or there's another one in here, which we multiply the first constraint with 1 over 3, and the second constraint with 1 over 3 again. Apparently, we cannot be larger than 5. So what am I doing? I'm making non-negative linear combinations of my constraints because all my x's should have to satisfy those constraints anyway. And by taking those non-negative combinations, I'm trying to imitate my objective function and get a bound of it. All right? As you see, I did find a very nice bound, 5. Yeah, this is a maximization problem. I would, of course, want to have a small bound, as small as possible. Infinity is a bound, yeah, all right. Or 10,000. Yeah, but apparently this problem can never have something larger than 5, which is a good bound, I guess, all right? So then what am I trying to do? I'm trying to find non-negative combinations of my objective function coefficients, all right, constraints. Each constraint gets a multiplier, and I'm trying to minimize what I get from them, right? So I'm trying to minimize their effect on the objective, while in the meantime, this is actually what they're supposed to satisfy. That's an interesting thing, but all I'm trying to do is I'm trying to write my objective function. These are the objective function coefficients on my original problem. As long as what I got from my constraints are larger than my objective function coefficients for this maximization problem, I can safely say that this is a bound, right? And that's all I'm doing. Now, this observation actually leads to a very crucial theory in optimization. That theory is what we call the duality theory. Well, I like to say this, associated with any LP, there exists another LP, which is called the dual. All right, be careful though. Associated with any LP, there exists another LP. So the duality is defined for linear programs, all right, which shouldn't have binaries or integers. But for any LP, we can create another LP. And these two LPs have very nice relationships within each other that we will utilize in our optimization search and methods. Now, knowledge of duality will provide insights into sensitivity analysis that we will come to that in a couple of weeks, which is what happens when you change the parameters. These are, again, some definitions, all right? I said, get an LP. That LP has another LP, which is called the dual. Well, then the original LP is called the primal, all right? So I have a primal and a dual. And we have primal-dual pairs because they're associated with each other. Now, the duality is defined for canonical forms. What is a canonical form? Canonical form max is this guy here, maximizing Cx subject to Ax less than or equal to B, X non-negative. Okay, this is the canonical form of the maximization problem. Remember, simplex works when this is equality. That's called standard form. But canonical form is when we have less than or equal to for a maximization problem, and every variable has to be non-negative. Okay. Now, the very first thing is, okay, let's look at this first. Okay, look at the objective. Maximizing, I have 2,000 variables, and I'm trying to maximize their summation as my objective function. All right. I have two constraints. The first one is x1 plus 2x2 plus 3x3 plus less than or equal to 1. And the second one is 1999 x1, 1998 x2 go like this, less than or equal to 100. Here's my claim. I'm claiming that my objective can never be larger than 101 over 200. Why? Well, just add these two constraints together, right? Then you will have 2,000 of their summations less than or equal to 101. And this is my objective function. Apparently, then, their summations cannot be more than 101 over 2,000, right? Again, a nice way to find a bound for the optimization that we're trying to do. Remember the canonical form, this is maximize Cx subject to Ax less than or equal to B, X non-negativity format. Let's see what we have then in an open form. Let me write it in here too. Maximize Cx subject to Ax less than or equal to B, X non-negative. The only thing that you should remember in taking the dual is for a maximization problem, the canonical form constraints are less than or equal to constraints, okay? We always have non-negativity. Okay, then this is my objective function, maximizing Cx. These are Ax less than or equal to B. These guys are Ax less than or equal to B. And we have X non-negative, okay? Now, what we do in taking the dual, I told you, every LP has a dual. So let me teach you how to take the dual of a given primal LP. What we do is we come up with multipliers for each constraint. That was the motivation, right? We come up with a combination of the constraints so that we represent objective function. Okay, let W1 be the multiplier for the first constraint, W2 for the second, Wm, because we have M constraints, all right? Okay, now as we have seen, this thingy becomes a bound for my objective, so I want to minimize it, minimizing WB then, yeah? So we're minimizing WB. Subject to, let's look, so what are we doing? We're multiplying, so for each variable in here, x1, Okay. I'm going to write a constraint. The multipliers should be less than or equal to the C1 so that the bound thingy works, right? So W1 times A11 multiplier and the coefficient in the first constraint, multiplier and the coefficient in the second constraint, W2 times A21, blah, 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 Wm times AM1 should be larger than C1, larger than or equal to C1. Yeah? And you do it for each variable. So this is the constraint for the second variable. And you go like this. So if you write it in the matrix form, this is what you're doing. Okay? So we just actually derived that, we defined the duality for canonical forms. If this is your primal, then this is the dual. We just take the dual in the previous slide, right? We're maximizing, if this is our original problem, maximizing Cx, subject to Ix less than or equal to B, then the dual is minimizing WB subject to WA greater than or equal to C. Everybody non-negative. Yes, Irmak?
Hocam, can you explain what happened to the objective function once again?
Objective function of the primal or the dual? I have two LPs right now, both. All right, the dual. Now, remember the bound thingy? Let me go back. One more slide, I guess. Yeah, remember I was trying to come up with multipliers so that when I do this, I still be larger than the 2 in here, so that I can safely say that the constraints thing will give me a bound, right? So that's what we're doing in here. Let me come back. So this is my primal. Let me clean and do it again. It's messy right now. Okay. So this is my primal, right? The one on the top. What am I going to do? I'm trying to find multipliers for each constraint. So each constraint gets a multiplier. Okay. And with these multipliers, and each variable gets a constraint in the dual, because all these will actually be bounds for me. Yeah. So all I'm doing is for each variable, I'm writing a constraint in here. So the constraint for X1 is W1 times its multiplier, W2 times its multiplier. W2 was for the second constraint, so I take the coefficient in the second constraint. W3 times its multiplier until Wm times its multiplier, okay? Well, this thingy should be larger than C1 so that at the end, what I got becomes a bound, right? And I'm multiplying the right-hand side of B1 again with this multiplier in the dual's objective. I'm adding them up because this summation will give me a bound. In the original example I put you, it was 2 by 2, so it was easy to come up with those multipliers. But in general, with an m by n system, you need optimization for doing that, okay? So that's all we do. We associate multipliers for each constraint in the primal, and then we write a constraint for each variable in the dual. Okay, so the variable x1, this is the constraint for x1. Constraint for x1, all right? This is the constraint that we have written for x2. Each constraint in each variable in the primal brings a constraint in the dual, all right? And each constraint in the primal brings a variable in the dual. That's why these are actually coming in pairs. So we have actually shown that if my primal is a canonical form max, my dual is a canonical form min. Okay? Any questions? Good. Now, let's look at this. All right? So this is my maximization problem in canonical form, as you see. I'm maximizing 5x1 plus 2x2 plus x3. My constraints are, this is my first constraint and this is my second constraint. What would we do? I said that we need to associate a variable for each constraint in the primal. That brings me W1 and W2. each constraint in the primal. I have two constraints in the primal. So I will have two variables in the dual, okay? Then I will write, let me change my color a little bit. Now I will write a constraint for each variable in the primal. So this is x1, right? These are the multipliers of x1. So I'm going to write a constraint for x1. W minus 1 times W1 plus W2 should be at least 4. This is for x1. Yeah? This is for x2 multipliers. 3W1 minus 4W2 should be at least 2. And this is for x3. W1 plus 2W2 should be at least 1. Okay? For each constraint in the primal, we have written a variable, associate a variable in the dual. And for each variable in the primal, we have written a constraint in the dual. So variables and constraints are actually associated in the primal dual pairs. Now comes the objective function. What is the objective function? Minimizing the summation of the two W's. Minimizing 10W1 plus 5W2. Okay? I'll explain what happens when we don't have a canonical form max. There is a question in the chat from Didam. I'll explain it in a minute, Didam. Okay? For canonical form pairs, well, then we have seen that they're actually primal dual pairs of each other. Canonical form max comes with a canonical form min. Now we're going to see we're going to see what happens in the for the rest in a couple of minutes. Any questions up until now in how I did take the dual? A variable in one corresponds to a constraint in the other. A constraint in one corresponds to a variable in the other. All right? Okay. The first theorem of duality. The duality comes with a couple of theorems that are pretty handy, actually. So the first theorem says the dual of the dual is the primal. All right? So the dual of the dual is the primal. Let's look at the proof. I usually like to do it on the board alone, but now that you have all the notes, we're going to go over the slides. So this is my primal. Currently, I only know how to take the dual of the primal. I don't know what's going to happen if I have equalities or reverse constraints. So I'll have to take my primal be the canonical form max. I know that the dual of this guy is this one, canonical form min. Yeah? So the primal, and this is the dual, minimize WB subject to WA greater than or equal to C, W non-negative. Now, this is okay, but I'm supposed to take the dual of this guy because it asks me the dual of the dual, right? But I don't know how to handle canonical form min. So let's convert this to a maximization problem. We can do that, right? Now, minimizing something is equivalent to minus maximizing the minus of it. Of course, you have to be careful where you're multiplying it from, right? So this minimizing WB is equal to, let's do it like this. So minimizing WB is equivalent to minus maximizing minus B transpose W transpose, because I'm multiplying everything with minus 1, and this is what happens in linear algebra, right? Okay. Canonical form has less than or equal to constraints, so I'm supposed to convert these constraints to less than or equal to, which what's happened in here. I'm multiplying with minus 1, which changes the inequality, reverses the inequality. But again, you have to be careful with the matrices, all right, from linear algebra. Okay, now this problem is equivalent to what's written on the left, right? Okay. So this was my primal. I take the dual. This is my dual. I'm supposed to take the dual of this guy. Well, I have just converted to an equivalent maximization form again. It's equivalent. Yeah? Now I can take the dual of this guy because it's max. I know its dual is going to be canonical form min. So I will assign a variable I will assign a variable for each constraint. Okay, let that variable be x, right? And I will write a constraint for each variable. So canonical forms comes within pairs for each other. So this will give me minimizing, but you have to carry this negative. It will be minimizing minus xtct, subject to I'll have a constraint for each variable, which is actually xtat greater than or equal to minus bt, which is, okay, change everything back to normal by multiplying minus 1 again. So you got the original problem. I take two duals and I got back. So the dual of the dual is the prime. Any questions in here? Be careful. We only know that the dual of this guy is this one, all right? Canonical form max and canonical form min. If your primal is canonical form max, your dual will be canonical form min, okay? So I know this. And then I'm supposed to take the dual of this. What I do, anytime, at any point, if you're supposed to take the dual, the only tool you have is the canonical form max form. So you're supposed to go to the canonical form max. So I take this minimization problem, convert it to an equivalent problem in the max format in canonical, all right? So I change my objective function, and I don't want the greater than or equal to sign, so I multiply everything with minus 1, all right? Then we have proved that the dual of the dual is the prime. Also observe here that we also take the dual. Let me clean it again. In this proof, during the proof, we actually take the dual of a minimization problem, right? Because this was the dual, and I was supposed to take the dual of it, and I take the dual of it. And this is what I ended up with. So this shows us that now I also know how to take the dual of a canonical form min problem, right? It's going to be canonical form max. So canonical form min and max problems are primal dual pairs of each other, right? If this is my primal, maximizing Cx subject to Ax less than or equal to Bx non-negative, my dual will be minimizing Wb subject to Wa greater than or equal to Cw non-negative. If this was my primal, this is going to be my dual. Yeah, these are primal dual pairs of each other. Now, this time, nicely, during the proof, I also learned that the minimization's dual, canonical form min's dual, is canonical form max. Okay? Any questions? Okay, then, let's, this is some sort of a review slide. So, for each constraint in the primal, I have a variable in the dual. Yeah. For each variable in the primal, we write a constraint in the dual, right? And if one of the problem is a min, the other one is a max in canonical forms. All right. So we started with this guy, canonical form max, and we have seen that its dual is the canonical form min. Also, during the previous proof, we have also shown that if canonical form min is my primal, then my dual is canonical form max. Okay? Any questions? I can re-explain any part. Okay. How about other forms? Yeah. Now we have seen that mins and maxes, and we only know the canonical forms. But in real life, in a normal LP, we will have many different variations, right? So, but as we have done in the previous proof, for each ambiguity, we're going to convert it to the canonical form version, and then we will drive what actually is going on, all right? So let's start with equality. If this is my primal, what's going to happen? Primal, maximizing Cx so that the constraints are all equality. It's a maximization problem with equality. Now, equality These are the tricks we have also used during the converting to standard forms, right? Well, equality means this, right? AX should be less than or equal to B, and AX should be greater than or equal to B. So this problem first equals to this guy in here. Maximizing CX subject to AX less than or equal to B, and AX greater than or equal to B. Now, I need canonical form, right? I need but let me write the canonical form here. Maximize CX subject to AX less than or equal to B, X non-negative. I require this format, right? So I don't want this. I have to convert this, multiply everything with -1. This is what happens, okay? And this is the dual. Now I can take the dual. Yeah, assign two sets of variables. Be careful, these are all sets, not just one variable. Now the dual of the canonical form max is canonical form min, but this is what happens. I'm taking the dual. I only have one type of constraint set X, so the dual will have a set of one type of constraint set. So the first one is W1A minus W2A greater than or equal to C, because I'm going to write a constraint for each variable. My variable X, so I'm writing my constraint like this. Now, remember, if you clean this a little bit, you can say that this is W1 minus W times B, and again, W1 minus W times A, greater or equal to C. They're both non-negative. Remember, we can make this change, and this was the trick we were using if we had free variables, right? Apparently, then, this is the dual. So what we have shown for equality, the corresponding multiplier, dual variable, will be free. Okay? We have just proved that for equality type constraints, the associated variables should be free. Any question in this proof? We'll have to deduct all ambiguities. What's going to happen if we don't have in the standard canonical form? So canonical min and max are primal dual pairs for each other. All right, that's on the side. Now we're having the ambiguities. Our first ambiguity that we discussed is equality. And we have shown that for equality constraints, the associated dual variable should be free, because we changed the equality constraint to less than or equal to and greater than or equal to. Then we change it so that everything is canonical form. And we work all the way through, and this tedious work shows us that the associated variable is free. All right? Any questions? All right. Now let's see what happens if I have a free variable at the beginning. The idea is the same. I'll utilize the same trick. We will represent that variable by the summation of two non-negative variables. And for every x, we're going to write x prime minus x double prime. You take the dual. Now you have two sets of constraints, two sets of variables. So you're going to have two sets of constraints. Canonical form max, canonical form min. Well, this thing is equal to equality. All right? So equality in one corresponds to the free variable, and free in one actually corresponds to the equality in the other. All right? Equality constraints, dual multiplier happen to be a free variable. And if you have a free variable in the primal, then the constraint that you're supposed to write for that variable will be equality. Any questions? Am I going too fast? Do you need me? Yes, Tolga.
Hocam, bu ikinci şeyde yaptığımız şey bütün x'leri mi etkiliyor? Bütün constraint'leri mi etkilemiş oluyor free olarak? Yani
if now you were writing a constraint for each variable, right? So if your variable that you're writing that constraint is free, then you were supposed to change it like this. And if you work it through, then the constraint that you're supposed to write for that x is going to be equality. All right. I mean, not everything, but if for every free variable in your primal, you're going to have an equality constraint in your dual.
Okay.
Okay. You're welcome. Any other questions? All right. So now we're driving the duals, right? What else can happen? Any ideas? What else can happen? Now I have dealt with equality and free variables. If my primal is maximizing Cx subject to right in the chat. What else can happen? This is my primal. I've shown you if this is equality. I've shown you if this is free. What else can happen? Oh, there's a question from Oktay saying that he couldn't get how we take the dual. All right, let me take the dual again, which is all the way. This is, I guess, a good example to explain how we take the dual. Over the example in the canonical form max. Okay, Tolga, can you lower your hand because I keep seeing it and you already asked your question if I'm not mistaken. Okay, thank you. Now, what did I say? This is my primal, right? Maximizing something, maximize should remain in here, subject to this. Now, I have to write a variable for each constraint in my primal. So I'm defining two variables because I have two constraints in my primal. W1 will be the multiplier of the first constraints thingies, and W2 will be the multiplier for the second constraints. Okay? Now, in the dual, I'm going to write the dual. Let's look at the constraints first. Okay? For each variable in the primal, I'm going to write a constraint in the dual. The variable is x1. Okay, I'm going to write a constraint for x1 in the dual. So x1, objective function coefficient is 5, and the constraint has -1 and +1. Okay, so the first constraint will be multiplied with w1. So w1 times -1. The second constraint will be w2, but it's a +1. So +1 times w2. This is maximizing Cx subject to Ax less than or equal to B, X non-negative. I'm supposed to get minimizing Wb subject to Wa greater than or equal to C, W non-negative. So Wa is in here, greater than or equal to C, which is 5. Okay? Objective function coefficient of x1. Second constraint is for x2. The first multiplier is 3. I'm writing Wa. 3 times W1 minus 4 times W2 should be at least 2. Okay. And W3, W1 plus 2 W2 should be at least 1. All right? So I have written my constraints. Objective function minimizing WB. W times 10 because this is for first variable, and W2 times 5 because this is for the second variable. Is it clearer now, Oktay? Because you asked in the chat, and I take the dual again, right? So if we go from here, each constraint in primal has a variable in the dual, and each variable in primal has a constraint in the dual. If one of them is min, the other one is a max. Okay, because we have seen that the primal dual canonical forms are primal dual pairs of each other. Okay. Then we were actually discussing what's going to happen if we don't have the canonical form, right? So, okay, this is canonical form, max. We have seen that its dual is canonical form min, and we also see if the primal is canonical form min, the dual is canonical form max. Okay. What happens if we have other thingies in our problem, like equality? So in this slide, we have seen that if the constraint, for each constraint, which is equality in the primal, the multiplier associated for that actually happens to be free. Of course, we will have a mixture at the end. Here, I'm just showing that if it is an equality, you're supposed to, well, we're just derived that the variable should be free. In the next slide, we have dealt with free variables, okay? If the variable is free, we have seen that the constraint, the associated constraint, because for each such variable, I'm going to write a constraint. So for each free variable, the constraint I have written will be equality, all right? Then here I had just asked, what else can happen? Yeah, we have seen canonical form min and max are primal dual pairs of each other. And then, so this is my canonical form max. And I've seen that this is the dual. Then we have also seen that if this is equality, I'm going to have the variable free. If this variable is free, I'm going to have the constraint free. What else can happen? Any ideas? You can chat, you can write from chat, or you can raise your hand. Any ideas? Is it done? Can you take the dual of anything? Negative variables. Very good, Ceren. Very good. We may have x less than or equal to 0. Yeah? Or there is one more ambiguity. One more. Any ideas again? From chat room, please. Come on. How about the constraints? Negative right-hand side, it's okay. It's just the b, so you can take, as it's -3, -3. This is not simplex. We're okay with it. Equality constraints, Tolgacığım, we just showed that they're going to come with free variables. Bigger than, exactly. Now, for maximization, this is the format, right? Maximize less than or equal to. Or for minimization, this is the format, canonical form version. How about if the constraint is in the reverse form? What do I mean? If this is it, maximizing Cx subject to Ax greater than or equal to Bx non-negative. This is not canonical form. I cannot immediately convert it. Now, the dual of this is not the canonical form and the constraint reverse. It's a different one. Let's see, because I guess it's the derivation right now. Oh, we start with negative variables. Okay, there are two more ambiguities that we need to go over. All right, let's start with negative variables. Maximizing Cx subject to Ax less than or equal to B, okay? But what if this is the case? X less than or equal to 0, all right? Then that's not allowed. This is not in canonical form. I have to convert everything to canonical form so that I can take the dual, right? So it's easy. I just make a change of variable. I define an x prime, which is the negative of it. And for every x I see, I write x prime. Okay, now my x prime is non-negative. And this is my problem. It's in canonical form. Let's take the dual. Then my dual is minimizing WB subject to WA greater than or equal to C, W non-negative. And, well, if you look at this constraint, this is actually equivalent to this one, WA less than or equal to C, W non-negative. So be careful for if the constraint is in the reverse format, okay, less than or equal to is reverse. If the variable in the primal is in the reverse format, then the corresponding constraint in the dual is reverse. Reverse. Not less than or equal to, greater than or equal to, because it depends what problem we're dealing with, but reverse. If the variable is reverse, the corresponding dual constraint will come reverse. Normally, I was going to write WB subject to WA greater than or equal to C, but since the variable I have written this constraint for is in the reverse form, the constraint is also reverse. Got it? So for negative variables in the primal, the constraint in the dual is reverse. Okay? This immediately should tell you what's going to happen if the constraint in the primal is reverse. Any ideas what's going to happen? Let me see the hands right now. Who wants to talk? If the constraint in the primal is reverse, like for maximization, if I have greater than or equal to. Any ideas what's going to happen in the dual? Let me see the hands. I still need participation. Yes, Vasik?
When the duality is applied and it turns into a minimization problem, then it's going to be WA is going to be less than C, so which is going to be like a proper normal duality problem.
So you're saying that if my problem is reverse canonical form, nothing will happen. I'll still have minimizing WB subject to WA greater than or equal to CW non-negative. Is that what you're proposing?
Yes.
Okay, who agree? Yes, Egeman, thank you very much. It is not correct because then this is the dual when I have this. AX less than or equal to BX non-negative. This is the dual for my legitimate canonical form max problem. If my problem is not in the canonical form, well, of course, something should be changing. This is what's happening right now. Let's see why it's true. Maximizing CX. If this is in the reverse form, this is not my canonical form. The only thing you should remember is the canonical form. Let me write the canonical. CX subject to AX less than or equal to BX non-negative. This is what I want all the time. This is my canonical form. All right? Now, if this is the case, then this is reverse. My constraint is reverse. So I'm changing it by multiplying -1. Now I can take the dual. This is in the correct form. I take the dual, and then you see I always have -w's around. You change the variable. With the change of variable, you're actually going to see that your dual variable, which is associated with a reverse constraint. I'm not saying less than or equal to, greater than or equal to, okay? This is very important. Always I'm saying reverse constraint. This is not the correct form for a maximization problem in canonical form. This is the reverse form for max. So my variable is reverse. It's not non-negative, it's less than or equal to 0, okay? Any question? Because we're just derived all the things that can happen if we have from the standard canonical form max gives canonical form min definition. We have derived all the types that can happen in an LP. So now I can give you any LP and the dual can be defined. Let's see. For a maximization problem, if ith constraint is less than or equal to, all right? It's a maximization problem. It's the correct version. Maximization, always write the canonical at some point, somewhere, all right? These are my canonicals. I will always have them around so that I will refer to them. So for a maximization problem, ith constraint less than or equal to. That's in my correct form, so my variable will be in my correct form because each constraint comes with a variable, right? If my ith constraint is equality, the corresponding variable should be free in the dual. If my ith constraint is greater than or equal to in a maximization problem, it's reverse. I want less than or equal to. So my variable will be reverse, less than or equal to. If my variable in the primal now is in the correct form, I want greater than or equal to, the constraint will be in the correct form. I want greater than or equal to. If my variable is free, the corresponding constraint is equality. If my variable is less than or equal to, the corresponding constraint should be reverse, and reverse for minimization is less than or equal Any questions? Any questions? Not all constraints should be greater than 0. All variables should be greater than or equal to 0, Simge. And we're not converting to standard form, we're converting to canonical form. Any questions? All right, try to take the dual of this in the break time. We will continue in the remaining hour. We will first take the dual of this guy, and then we will start the other set 6, which is duality theorems. If you have any questions, ask. Otherwise, we're going for a break for 10 minutes.